So this week you've been introduced to new concepts like heat of fusion. Anyone tell me what heat of fusion means? It's not a good sign. Heat of fusion, what would that mean? Or what's fusion mean?
Is it kind of like the connection of like molecules due to heat or something like that?
It definitely involves a connection between molecules. It involves a connection between two different states of matter. So which two states of matter are we talking about when we're talking about fusion?
Solid and liquid?
That's right, exactly. So it's the amount of heat involved from transitioning from solid to liquid. Just like the heat of evaporation is involved in the process of changing from what two states?
Liquid to gas.
Exactly. So when we look at heat capacity of something, that we look at the heat capacity of a gas, we look at the heat capacity of a liquid, we look at the heat capacity of a solid, and we have to think in terms of how it changes as the temperature changes. But what's different about freezing or boiling? Do they happen at different temperatures?
Yeah.
You're right, but that's not, I realized I gave a really bad question there. Let's look at does the freezing point of water, is that different or is that constant?
Constant.
That's constant, right? So that is, I'm sort of talking way too much about the last question. I figured we'd do that one together because we can see that during phase transitions, as we add more heat, the temperature doesn't increase, right? You may have noticed that if you're boiling, if you took the temperature of a pot on a stove, the water goes up to like 100 degrees Celsius, and then it just stays there. You can add more and more and more and more heat, but it doesn't get any hotter until all the water is gone. So we'll look at that in terms of the last question. But before that, does everyone have their recitation? Again, I think I posted it this time.
Yeah, it's in there.
Yeah, it only took me all year to finally remember to post it. So, we're all learning. So here is the recitation. I figured we would do a couple together, and then we go into a couple rooms and then all come back. So are there any of these in particular people had trouble with before we go into our groups? So you've been learning about intermolecular forces, right? And hopefully learning that it's the intermolecular forces that basically are responsible for boiling points, freezing points, because it's you have to break those intermolecular forces between molecules for them to transition from a solid where they're in close contact to each other, to a liquid where they're in slightly looser contact with each other, to a gas where they have no contact at all. And so for those substances that have very little intermolecular force between them, like helium atoms, they will be a gas at extremely low temperatures because there's hardly any force at all existing between those. Contrast that to water molecules, where there is a really strong interaction between them. The freezing point and the boiling point are much, much, much higher. So let's just quickly look at a couple of these. So benzene, for instance. Anyone tell me what benzene looks like? We've looked at benzene before. What kind of molecule is that?
A hydrocarbon?
It definitely is. It's a special kind of hydrocarbon. We call it an aromatic hydrocarbon. Anyone remember what an aromatic hydrocarbon is?
It has scent.
It has a scent. It has a strong scent. But chemically, what's an aromatic hydrocarbon? It has special kind of bonds.
They're like a ring.
That's right. It has a ring. It looks like this, where we can draw it like that, or we can draw it like this, with hydrogens at each point. And so instead of having a double and a single and a double and a single, we finally realized that it's best to draw it like this, because each bond has a bond order of 1.5, rather than a single bond, which is a bond order of 1, or a double bond, which is a bond order of 2. If you actually look at benzene, each one of those carbon-carbon bonds is exactly the same distance. A little longer than a single bond, or a little longer than a double bond, a little shorter than a single bond. So it's sort of in between. So if I have two of these things together, what kind of intermolecular forces can I have interacting between them? Can I have hydrogen bonds? Remember, there's hydrogens at each point. So can those two hydrogen bond with each other?
No,
No. How come?
because hydrogen only has one valence electron.
Hydrogen always has only one valence electron. It depends on who the hydrogen is bound to. What does hydrogen need to be bound to in order for it to be able to hydrogen bond?
Nitrogen.
It can be bound to nitrogen. That's one. What's another one? That's the classic one.
Oxygen.
Oxygen, right, and water. So it can be bound to hydrogen, sorry, it can be bound to nitrogen, oxygen, and the other one is fluorine. And here it's just bound to carbon. So it can't hydrogen bond. So that's out. So what other interactions can we have? What are some of the other interactions? What are some of the intermolecular forces?
Dispersion.
Dispersion. What is the dispersion interaction?
It's like when they're temporarily asymmetrical, so they create dipoles.
Excellent. Yeah. Basically, it's the interaction of last resort. It's the one interaction that any two molecules can form, because there's always a possibility of a spontaneous dipole that can form at any moment. So yeah, dispersion forces. So we can say that just by default that these two can interact by dispersion forces, because any two molecules can interact by dispersion forces. It's the weakest interaction there is. What about, are there any dipoles in this molecule? Can we have a dipole-dipole interaction? Is that possible? Are there any dipoles in a benzene molecule?
Don't they cancel each other out?
Yeah, there's pretty much, there aren't any dipoles, really. The difference in electronegativity between carbon and hydrogen is really, really, really small. So even if there is a dipole, it's extremely small. So not really. So there's no dipole. What about, then there's no ions, right? We can't have an ion dipole interaction because there's no ions. There's no dipole-dipole interaction. There's no hydrogen bonding. So pretty much what's the only thing left?
Is it only dispersion?
Yeah, it's pretty much it. It's pretty much only dispersion. But the bigger the molecule, remember, the bigger the molecule, the greater the dispersion interaction. So here we have 6 carbons and 6 hydrogens. And if you remember, I don't know if we really talked about it, benzene is planar. It's flat. It's a flat molecule. So if you have one flat planar benzene molecule and another flat benzene molecule right next to it, that's quite a lot of surface that comes in contact with each other, which is why benzene is a liquid at room temperature. So there is enough dispersion force. Remember, dispersion forces are additive. If you have a really big molecule, like candles, remember we looked at burning candles earlier, and we tried to balance that equation, and you looked up what the formula for paraffin was. Well, paraffin has a lot of carbon and hydrogen. That's also hydrocarbon with no dipoles in it. But at room temperature, it's a solid. Why? It's only dispersion forces. Yes, but paraffin, the molecule, is so big that just the weak dispersion forces, if you add enough of them together, it's enough to hold it into a solid shape even at room temperature. So we can't discount dispersion forces because we can add them together. So for benzene, just dispersion forces is enough to keep it a liquid at room temperature. So let's have a look at the next molecule. Let's just draw it out. Here we have chloromethane. So what kind of interactions would chloromethane have with another chloromethane molecule? So first we have to look at what sort of, are there any dipoles in this molecule?
Yes.
There is, right? So this is this a polar molecule or a non-polar molecule?
Polar.
It is polar, that's right. Oops. This is a polar molecule. This is also a liquid at room temperature. So where is the dipole? Between what two atoms would we find a bond dipole?
The carbon and the chlorine.
That's right. Which one's more electronegative?
Chlorine.
Chlorine's more electronegative, right? So our dipole will be here. So if it's so this chlorine would be slightly negative. This carbon would be slightly positive. So what kind of interaction would chloromethane have with another chloromethane molecule?
Dipole.
That's right. And have a dipole-dipole interaction. What else? Anything else? Can it have an ion dipole? Could it hydrogen bond?
No.
So there's no ions because it's only a partial charge, so that's out. And it can or it can't hydrogen bond?
Can't.
It can't, right, because the hydrogens are bound to carbon, so that's out. So we have a dipole-dipole interaction. Do we have anything else?
Dispersion.
We always have dispersion. There you go. Yes, always. So whenever you have a question like this, list the types of intermolecular forces. Always put dispersion down first, because you'll never be wrong, because that interaction is always present. So you can always do that. But then on top of that, you can do other things. So the two for chloromethane would be dispersion, because that's always there, and then dipole, dipole. All right, let's just look at water, because water, as you all know, is my favorite molecule. It's the most important molecule in the world. So let's draw it. So there's our good friend water. So we know it has dispersion, so get that out of the way. What other interactions does water undergo?
Hydrogen bonding.
It definitely can hydrogen bond. So hydrogen bonding is unique. It is a unique kind of dipole-dipole interaction, because what it is basically two water molecules basically sharing a proton. So this oxygen has a slight negative charge. This oxygen has a slight negative charge, and this proton, or this hydrogen, has a slight positive charge. And so we have this very strong, now a hydrogen bond is much stronger than just a typical dipole interaction. So basically what a hydrogen bond is a bridge between two dipoles. So hydrogen is sort of stuck in between two dipoles. So that's why it's such a strong interaction. So we've got dispersion, we've got hydrogen bonding, and what else? Anything else?
Dipole, dipole.
Well, that's an interesting question. I don't know whether we would say that a dipole-dipole interaction exists independently of a hydrogen bond, because the only dipole-dipole interaction involves protons. So these two molecules would have a hydrogen bond, and then another water molecule would be here, and that would form another hydrogen bond. That's basically, so each water molecule can form like 3 hydrogen bonds, and there'd be another water molecule down here and another hydrogen bond. That's why water is such a high boiling point, because each individual molecule of water has the potential to form 3 different hydrogen bonds with other water molecules. So I don't know. I will look that up. I think we just say it has dispersion and hydrogen bonding. I don't know if we would include dipole-dipole, but I will find that out before the end of the class. All right, let's look at the last one. So here we have carbon disulfide. So we've got carbon. So what sort of interactions are possible here? First question, do we have any dipoles?
No.
Are you sure? We have bond dipoles. Doesn't mean we don't have, you're right that we don't have a molecular dipole, but do we have any bond dipoles?
Yeah, and then they cancel, right?
Yeah, we do, right? We have a couple of them. We got one here, and we got another one here. So there is no net molecular dipole. That is true, because we have equal and opposite bond dipoles. But we do have molecular Well, we do have bond dipoles going in opposite directions. And so this carbon is slightly positive, actually more than slightly positive, because it has two sulfurs pulling electrons away from it. And these two sulfurs are slightly negative. So we know we have dispersion, because we always have dispersion. Can we have dipole-dipole interaction here?
No.
Why not? I've got a slightly negative charge on the ends, and I have a slightly positive charge in the middle. What if I had another yes. What about this interaction?
So yes.
Yes. Yeah, we can have a dipole-dipole interaction here. Each individual molecule does not have a net molecular dipole, so it's non-polar. But there are two dipoles in that molecule, and so there's really nothing to keep this slightly negative sulfur interacting with this slightly positive carbon. They would sort of be at a 90-degree angle to give you the best interaction. So that does exist. So carbon disulfide is a liquid at room temperature because of that interaction. It's not a very big molecule, so we don't have a tremendous amount of dispersion forces, but we do have a fairly strong dipole-dipole interaction. Okay. So are there any other, let's have a look at the other problems. I think you can probably work on this one. We can look up the melting point for someone in the group can look up the melting point and explain in terms of the different intermolecular forces between them. We have, third one is basically the same question. You have three different molecules here, and then arrange them in the way you think their lowest boiling point to highest boiling point. In other words, which one is the lowest intermolecular force interactions, and then which one would have the strongest. And then I figured I would do one of these with you, and you could do the other one in the group. And then I'll do the last one with you at the end, okay? So why don't we look at this one together. So have you guys looked at this equation in class or during the lectures or during any of the discussions you've had with Professor Schubert?
No.
Yes, no? Is this new? This equation?
We didn't go over it on Tuesday.
I'm gonna have to close my window because there is work going on outside. It is very loud. So let me take care of that. So this equation basically relates the heat of vaporization. So what is the heat of vaporization? What does that even mean?
Like turning a liquid to a gas?
Right. And because it's delta H, what does that tell us?
Change in enthalpy?
Mm-hmm. It's a change in enthalpy. But when we see a delta and a capital H, what does that immediately mean? It means enthalpy. That's exactly right. But what does the capital H stand for?
Does that mean heat is being added?
No, sometimes it means heat is being taken away. Delta H can be either positive or negative. In this instance, it's positive because you have to put heat in to vaporize something.
Is it the change in heat?
It is a change in heat. But look at the first, number 1, just read that and tell me what delta H means.
Per mole.
Per mole, exactly. Delta H always means per mole. Q is heat also, but Q is the amount of heat involved in any reaction with involving any amount of stuff. Delta H always refers to per mole. So when it says estimate the molar heat of vaporization, it means you need a mole of stuff. How much heat would it take to evaporate a mole of a liquid to a gas? Or if it's something like dry ice that doesn't go through that transition, just goes directly from a solid to a gas. What do we call that when it goes directly from a solid to a gas?
Sublimation.
Sublimation, exactly. So that would be the heat of sublimation. So,
Can I ask a question?
sure.
So since enthalpy is per mole, does that mean that you could always find enthalpy by dividing the amount of heat by the number of moles?
That's exactly what it means. That's exactly what it means. So delta H, that means that if you do an experiment with like a gram of the liquid, and I do the same experiment, but with 2 grams of liquid, my value of Q will be twice as much as yours because I have twice as much stuff. But when we convert it back to moles, you and I should get exactly the same answer. So that's why delta H is always in moles, so we can get the same, we can compare our results, okay? So what this, oh, go ahead.
I thought for enthalpy you had to account for work in addition to heat.
Yep. But usually, not always, usually when we're looking at enthalpy, no work is being done because generally the pressure doesn't change, or we're not creating a gas, or if the pressure doesn't change, or the volume doesn't change, or the amount of gas doesn't change, like we had 2 moles of gas as reactants, we have 2 moles of gas as products. We don't have to worry about it. So usually we don't include work. We should, but if there's no change in pressure, then there's really no work being done. For instance, when we are boiling water, the water goes from a liquid to a gas, but it all happens at 1 atmosphere of pressure. And so the volume increases, but we're not controlling the volume. So the water's just boiling off. If you have a pressure cooker, work is being done there because you're increasing the pressure. That's why the boiling point of water is much higher when in a pressure cooker. It's why a pressure cooker cooks food much faster, because the temperature is much greater. Because in order to evaporate that water under high pressure, you need a much higher temperature. So if we're just boiling water in a pot, we're not really doing any work. And so we just look at the amount of heat only and not work. But that's an excellent point. You really need to consider work, but that only happens when the pressure changes or the volume changes. And in this instance, they don't. Okay?
Okay, thank you.
No problem. Excellent question. So here, so this equation basically shows you the connection between vapor pressure and the heat of vaporization. What does vapor pressure mean? What does that mean?
Is it the pressure from the vapor?
It's the pressure from the vapor at a particular temperature. That's the key. Like, what is the vapor pressure of water at 100 degrees Celsius? In atmospheres. Shouldn't have to look it up. It's basically, it's the definition of a boiling point.
1 atmosphere?
That's right. That's right. At 100 degrees, the vapor pressure of water is 1 atmosphere because it's transitioning from a liquid to a gas. And so that pressure is the same as whatever the pressure is. That's why the boiling point of water is lower in Denver, Colorado than it is in San Francisco, because the pressure is different. So the vapor pressure of water at, let's say, 88 degrees in San Francisco is less than an atmosphere. It'd be about, like, I don't know, let's say it's like 0.9 atmospheres or something. But in Denver, it's 1 atmosphere. So your water is boiling at a lower temperature because the overall atmospheric pressure is lower. That's why the boiling point is lower. That's why there's all these different recipes for like cakes and pies and everything when you're doing it baking at a higher higher, what am I saying? When you're up at a increased, footage, you're way up there, at a mile high or whatever it is. All your temperatures are changed for heating and baking and cooking because all of the atmospheric pressure is lower, and so your partial pressure from water is different. So everything's different. So this tells us what the relationship is between vapor pressure and the actual heat in order to vaporize an entire mole of something. So let's have a look. So it says, estimate the molar heat of vaporization of a liquid whose vapor pressure doubles when the temperature is raised from 75 to 100. Okay, so you can see we have T2 and T1. Those are just the 2 different temperatures. So T1, let's say T1 is 75 degrees and T2 is 100. So P1 would be that pressure at temperature 1, and P2 would be that pressure at the higher temperature. So all we know is that the vapor pressure doubles. So P2 equals 2 times P1. So the ln of P1 over P2 is 1/2, right? Because we have P1 over 2P1, so that's 1/2. So what is the ln, natural log? You know what the ln means, right? It means natural log. Is that new information for folks? Do you know how to,
I don't think so.
you know how to find the natural log of something?
Yeah.
Okay, good. So the ln of 1/2 is equal to delta H, vapor, so our molar heat of vaporization, divided by R. Now R, we got to be careful here. This is not the same R we've been dealing with. This is not the gas law R. Different R. Wish they'd come up with a different letter, but they didn't. So that's a little confusing. Students will look at that and say, R, oh, right, that's 0.821 moles and liters and atmospheres and joules, but this isn't that particular R. So anyone know what the value of R is there? What's R in this particular situation? Because it's going to be relating joules, moles, and temperature. So there's no atmospheres here. So that's how we know that we're not dealing with the gas law R. There's no atmospheres in this particular equation. There's joules, for the heat, there's T for the temperature, and there is moles because it's a molar heat. So this particular R, and I think if in a test you'll just be given it, it is 8.314 joules per Kelvin per mole. That's the value of R. So again, you won't have to memorize that. Just know that it's not the same as the gas law R. So that part's a little confusing. So now this is just basically a plug and chug kind of situation because we know what R is.
So does that R change every time?
It depends on, no, this value of R is the same for all of these sorts of equations,
Okay.
but it's not the gas law R. That's the only thing you have to remember. The gas law R has atmospheres in it.
But it is a constant.
Yes. Well, that's why it's an R. R basically stands for constant.
Gotcha.
Yeah. R stands for a constant, but the units are different. So that's why I always try to include the units, because that tells me what value of R I'm looking at. Is it joules per Kelvin per mole? That's 1 R. Is it moles and liters? Yeah, there's no liters in this either. So that also tells us it's not the gas law R. So ln of 1/2. What's the ln of 1/2? Natural log of 1/2. Someone must have a scientific calculator. I don't have a scientific calculator. I actually had to Google it. If you go to Google, it pops up with a scientific calculator.
Negative 0.6931.
Yeah, 0.69315. So that is equal to delta H vape divided by 8.314 joules Kelvin moles. And then, so what do we put down for T1 and T2? Do we use these numbers?
You would use kelvins?
That's right. It tells right here. It's right in the value of R. That's K. It's not degrees C. And really, anytime you're dealing with gases, you always use Kelvin because it's an absolute scale. So we have to convert T1 and T2 to Kelvin. So 1 over T2 minus 1 over T1. What's my T2 going to be now?
373.15.
373.15. And my T1?
348.15.
So 373.15, and this is, right, 348.15. And I subtract those two. So let's see what that gives us. So I'm going to get 0.6315 equals my vape divided by 8.134 joules per Kelvin per mole, multiplied by, and I did this earlier, 0.00. Here's where you get the really small numbers. 268 divided, or subtracting 0.002872. 2872. Like I said, this is basically you just plug in the numbers and then you go through it. Thing to look at is make sure you get the signs right and you get the units right. Because these units, these are going to be weird units here. These are going to be in reciprocal 1 divided by K. because we took two temperatures. Remember, we have two temperatures here. So they're both 1 over K. And so we subtracted one over K by another 1 over K. So our unit here is 1 over K. So when we do the math, that is minus 0.00192. So I multiply both, or sorry, I divide each side by 0.00192, and I'm left with 3,610.1 equals delta H VAP over 8.314 joules per Kelvin per mole. And since I divide it by 1 over K, I now have K over here. My K's cancel, and I'm left with joules per mole, which is what I want, basically. So then I just multiply each side by 8.314 joules per mole, and I wind up with 30,015 joules per mole equal delta H vapor. So when I convert that to kilojoules per mole, what do I get?
$30.015.
Yeah. I just put a decimal point right there. So how many significant digits should I give?
Two.
You sure? How many significant digits are in the temperatures?
One.
One. Yeah, there's two significant digits here, and there's only one significant digit there. So really, you can only give one. So your answer would be 30 kilojoules per mole. So notice we wound up with a positive, right? We had negative on each side. We had a negative here, and we had a negative here. And so you end up with a positive. And that's what you want, because it takes heat to vaporize something from liquid to a gas. That's a positive thing. You need to add that heat in there. That's a positive. So if you wind up with a negative, you've probably done something wrong. Go back and double check. So basically, this is just, you have a formula, just plug the numbers in. But just be really careful with positive and minus, and make sure you know what make sure you get your natural log right. Because it's really easy to flip it from positive to negative. Like if instead of like ln of 1 over 2, you might have done ln of 2. That's a positive number. And so you might have wound up with a negative result, okay? All right, so I'm gonna divide up everyone into the 2 rooms. You can work on the other problems. The last one we'll do together, okay? The last one we will do as a group. So, yes, John, it was altitude I was looking for. I was just having a brain fart there. All right, let's allow everyone to share. Benjamin, you're with us today.
I'm here, Professor.
Make you a co-host. And so how many people? We have 12. Let's do, yeah, just do 2 rooms then. And so, yeah, let's work for, I don't know, 45 minutes or so. And then we'll come back. Obviously, Benjamin and I will come in and see if you're having issues. But then I want to leave like, about 20 minutes or so for the last question, because it's a long question. So for this problem, so no one actually did this one?
No.
Okay. This was really pretty straightforward. Do my annotation. So what does delta H sub mean? What does that actually mean? Delta H sub, CO2.
Enthalpy of sublimation.
Oh man, Marissa, you're killing it. Yes, sublimation. So that is the amount of heat required to basically get solid CO2 to convert to gas. So we have dry ice. So we start with dry ice. And we want to figure out if we have 1 mole of dry ice, how much heat is going to be taken out of, since this is positive, right? And we remember that whenever heat is lost somewhere, heat's gained somewhere else. So as carbon dioxide goes from a solid to a gas, it takes that as a positive 25.2 kilojoules per mole. So what that means is it takes 25.2 kilojoules per mole out of the surroundings. So the surroundings go down by 25.2 kilojoules per mole. And so we've basically lost 25.2 kilojoules per mole. That means, what does delta H fusion of water, what does that mean? So delta H fusion, what does that refer to?
Like the heat required for water to fuse with another substance?
Not with another substance. Remember, it's positive here. That's positive, not negative. So that means what you're adding heat. So if you're adding heat to water and it's fusion, what 2 states are you moving between? So fusion, we know it's going from a solid to a liquid, right? That's what fusion means. Right? Are we on board with that?
Yes.
So when we add 6.01 kilojoules per mole, that's the amount of heat it takes to change liquid or solid water to liquid water. That takes heat, right? We have to add heat. So we take ice out of the fridge, it starts to melt because we're adding heat. The heat from the room is going into the ice and turning into a liquid. Well, to go backwards, we need to take heat out. So in order for this reaction to go the other way, we need to remove heat. And that's what happens in your freezer, right? We're taking heat out of the surroundings and we're turning the liquid into a solid. That is negative 6.01 kilojoules. That's how much heat we need to remove from liquid water to turn it into a solid. Well, how much heat is being removed when carbon dioxide solid turns into carbon dioxide gas? The answer is negative 25.2 kilojoules. So if I have that much heat removed when dry ice turns into a gas, and I need this much heat removed to turn liquid water into a solid, well, how many moles of water can I freeze then?
So you would divide 25.2 by 6.01.
That's right. That's right. Because 25.2 kilojoules divided by minus 6.01 kilojoules per mole. My negatives cancel out. My kilojoules cancel out. And I have 1 over moles. Well, that's moles. So it's just a little over 4 moles. So 25.2 divided by 6.01. That's 4.19 moles. And then let's multiply that by Avogadro's number to get molecules. So that question is fairly straightforward. The confusing thing about it is remembering the difference between positive and negative. The heat of sublimation is the amount of heat you need to put in to turn it from solid to gas. If you're going the other way, then that's negative. Same with the heat of fusion of water. That's the amount of heat you need to put in to turn it from a liquid or from a solid to a liquid. If you're going in the opposite direction, it's also negative. So if I want to freeze carbon dioxide, I need to remove heat. That would be negative. If I want to freeze water, I need to remove heat. That's negative. Okay? All right. So let's look at the last question. So this is a classic question to put on an exam. I usually put this as a bonus question on my exams, except I put a lot of extraneous information in there to make it as confusing as possible. But this is a question you need to look at really carefully and take step by step, because there's a lot of things going on here. Because what we're asking is, we've got 866 grams of ice, and the temperature is minus 15. And so we want to convert all of this into steam. That's gas, and 146 degrees C. So there's a lot going on. So what's the first thing we need to do with our solid ice, our solid water at minus 15 degrees? What's the first thing we need to do with that? Because there's a lot of transitions going on. What's the first transition?
Solid to liquid.
Mm-hmm. But that's the first phase transition, but there's something we need to do to the solid water first before we can get to a phase transition, isn't there?
Convert to moles.
Nope. We do need to convert to moles. Yes, we can start with that. We can start with how many moles of water that is. That's a good point. So we have 866 grams of water. So how many moles is that? So that's 866 grams divided by how many grams per mole? It's like 18, right? Oxygen 16, hydrogen's 2, so
18.015.
yeah. 18.015 grams per mole. So how many moles is that?
48.071.
Moles. Okay. So now we have 48.07 moles. So we'll use that. Actually, we'd only use 3 significant digits, but remember, when we're doing calculations, we carry as many significant digits as we want through the calculations. Carry all of them until you get to the end, and then you round off. So that's how many moles we have. So yes, so we considered moles. We know that our phase transition is going to be from solid to liquid. But something else has to happen first. What has to happen first before we can have a phase transition from solid to liquid? What temperature does that transition take place? Does it happen at minus 15?
100 degrees Celsius?
That's the boiling point of water. We've got a solid and we need to turn it into a liquid. So what temperature are we looking at for that phase transition? Solid to liquid. What temperature is that?
John said 0.
Right, because that's the freezing point of water. It's also the melting point of ice. It's the same thing, right? So that's the temperature at which water freezes, and it's also the temperature at which ice melts. So the temperature of freezing water is 0. The temperature of melting ice, 0. That's because the phase transition takes place at 0. So we can't just convert solid ice to liquid water at -15. We need to heat it up to 0 first, right? So I would say that is the first thing we need to do. First thing we need to do, heat solid to 0. What's the second thing we need to do? What's the second part where heat is going to be required?
From water to water vapor?
Nope. That is a step. It's not the next one, though. Actually, I'll write that down. It's okay. So you said to turn the liquid into water, right? So we need to convert liquid to gas. Is that what?
Yeah.
Okay. What's another step? Oops. I think we're missing a couple. So we need to heat our solid up to 0 so it can melt. What else do we need to do? We need to convert the liquid to a gas. That's true. What are some other steps we need to do? Need to check my chat because I'm sure Jean has all the right answers. That's right. That's right. Sean's always on top. That's right. We need to heat the liquid to 100 degrees. Because we can't just go from very cold water to a gas. We need to heat the liquid to 100 degrees C. That is absolutely correct. What else do we need to do?
You'd have to calculate the change in heat, right? Change in temperature in order to find the heat required to turn the ice into liquid and then the liquid to gas.
So we need to, well, we know what the temperatures are. The temperatures are 0 and 100. So we know how much that, so that's where our phase transitions take place. But we're not done. There's still two things we haven't done yet.
So you have to find the heat, the amount of heat.
Well, that's the overall question, is how much heat. But I'm saying there's two things we haven't considered calculating yet. So we need to heat the solid to 0 to get it to melt. That's correct. We need to boil the liquid to a gas. That's true. We need to heat the liquid at 0 up to 100 so it can then boil into a gas. But there's two more things that we haven't considered yet. What's the final temperature we need? Because remember, when we boil the liquid water into gas, it's going to be 100 degrees C, right? Is that the final temperature? Have a look at the question.
So you would you would increase it by 46 degrees.
Right, we need to heat the gas from 100 to 146. There's still one more thing we have not considered. So if I was to draw, let me draw a diagram for you. Maybe it will help. So here I've got time or heat. This would be Q. This is the amount of heat I'm putting in. And this is the temperature. Oops, what the hell happened there? And this is the temperature over here. So I would start with my solid. I'm putting heat in, and it turns to liquid. And then I heat my liquid, and it turns to a gas. And then I heat my gas. So that is 1, 2, 3, 4, 5 different things we need to do. We've only listed 4. Which one are we missing? So notice there's 3 areas where the temperature increases, and there's 2 areas where they don't. When doesn't the temperature increase when we're adding heat? What's happening then? Let's look at number 4. What's actually happening there? What's physically occurring? We're putting in heat, the temperature is not increasing. What's physically occurring there?
Evaporation?
That's right. This is a solid. This is a liquid. This is a liquid. This is a liquid. And this is a gas. So at that point, during number 4, liquid is turning into a gas. That is a phase transition. And during a phase transition, the temperature doesn't increase because we're taking a liquid and we're converting it into a gas. And so the temperature doesn't increase until all the liquid's gone and I only have gas. And then the temperature starts going up again. So the temperature doesn't change during a transition, but it requires heat. It still requires heat because I'm still converting liquid to gas. The temperature's not changing, but I still need to keep adding heat because, like, if I have a pot of boiling water and I want to convert all of that water to steam, I need to keep boiling it till all that water's gone, right? That takes more and more heat to do. So if I turn off the stove, that transition stops, right? I still have liquid left over. So this temperature doesn't change till all the liquid's gone, and now I've got gas. What's happening during this transition?
Melting?
Melting, right. We forgot to include the heat involved in melting. So we haven't melted the ice to liquid. That takes heat. So we heated up the solid, we heated up the ice until it got to 0, because that's what we need to get it to for the melting process to start. But we forgot that we needed to add more heat to turn all of that ice into liquid. So once all that ice is converted to liquid, then the temperature starts going up again. Because now I don't have any more solid ice. It's all converted to liquid. Now the liquid is being heated up so I can get it to the next phase transition, which is boiling from liquid to gas. So we forgot to convert solid to liquid. So that's why this question is so hard, because there's like 5 different things going on. So let's put them all together. So I start with my 866 grams of ice at minus 15. So the first thing I need to do is raise the temperature to 0. So what information do I need to figure out how much energy that is? I'm raising the temperature of something. So what do I need? What information do I need to calculate this?
The mass,
Yep, I need the
engine
mass.
temperature.
So I need the mass, 866 grams. What else do I need?
Change in temperature.
My change in temperature is 15 degrees.
And heat capacity.
The heat capacity, exactly. Which heat capacity?
Of water.
Which water?
Solid water.
That's right. Because the heat capacity of ice, the heat capacity of liquid water, and the heat capacity of steam are all different, right? Because they're in different states. And so they go from one, it takes different amounts of heat to change the temperature of each one. So liquid water is the most difficult to increase. You need to add the most heat to raise the temperature of liquid water. Solid water, it takes less heat to get it to change temperature. So the heat capacity for solid water, or heat capacity ice, is 2.03 joules per gram per Kelvin. So now I have all the information I need for that very first step. I have the mass of the ice, I have the change in temperature of the ice, and I have the heat capacity of the ice. Because remember, Q is mass times heat capacity times change in temperature. So what's this number? Man, you're gonna make me do my own calculations. This is just not right. Sean asked, shouldn't we change degrees to Kelvin? I'm saying you don't have to. How come?
Because the change in temperature is the same whether it's in kelvins.
Exactly. So I could change minus 15 to Kelvin. I could also change 0 to Kelvin. But then when I subtract them, I get exactly the same answer. So the difference between minus 15 and 0 is exactly the same as if I add 273.15 to each one of them and subtract them. I get the same answer. So yes, if you want to be absolutely sure, you can convert it to Kelvin, but you don't really have to because you're just subtracting them. Good point. What's the amount of heat I need for the first step? Gee, I guess I'll have to do it myself. It is 26,370 joules. Okay. So I got my first, that's the first amount of energy that goes in, 26,370. What's the next thing that happens? So now I have my 866 grams of solid ice. It is now liquid at 0 degrees. No, wait a minute. Now it's a solid at 0 degrees. What's the next thing I have to do? So I have gone from a solid at minus 15 to a solid at 0. What's my next step? I still have solid ice. It's at 0, but it's still solid. So what do we have to do now? Come on, John, help me out here. That's right. We need to convert H2O solid to H2O liquid. What information do I need to solve that? Is that a heat capacity problem? Do I need the heat capacities for solid and liquid to do that? Or what do I need? What information from the question do I need to solve that? This might help. At 0 degrees, at 0 degrees. What information, do I need heat capacities, or what do I need to solve converting 866 grams of solid water to liquid water? I'm trying to solve for Q, John. So I'm trying to solve for Q. I need to, how much heat is involved in changing that much solid water to that much liquid water? And remember, the temperature is not going to change. I'm just changing the phase of the water from solid to liquid. So it's actually, it isn't a heat capacity because there's no change in temperature. And remember, with a heat capacity, we always consider a change in temperature. So this isn't a heat capacity question. What am I literally doing here? I'm changing from a solid to a liquid. So that is a heat involved in a phase transition. Which phase transition is it? I'll give you a heat. I'll give you a hint. It's one of the delta H's. Which one is it? Is it delta H fusion, or is it delta H vaporization? Delta H fusion, that's right. Delta H fusion is the amount of heat involved in the transition between solid and liquid. That's what delta H fusion means. It's how much heat do you need to add to a solid to convert it to a liquid. It's also the amount of heat you need to remove to turn a liquid back into a solid. But in this instance, we need to put the heat in to change it from a solid to a liquid. So delta H fusion is positive for us. Another difference you'll notice between delta H fusion and heat capacity, not only is there no delta T for delta H of fusion, but because it's a delta H, we're not dealing with mass. What are we dealing with when we see delta H? It's not mass we're dealing with. It's not pressure. Capital H, moles. That's right, Dennis. It's moles. So we need to take our grams and convert it back to moles. So we already know that it was 48.07 moles of H2O solid that we need to convert to H2O liquid. So Q is going to be equal to the delta H fusion times the number of moles. Delta H fusion is 6.01 kilojoules per mole times 48.07 moles. Moles cancel. And now I've got 6.01 times 48.07, 288 kilojoules, 288.9 kilojoules, 288.9 kilojoules. Okay. So now I have two things we've calculated. Fortunately, we still got 3 more to go. So at this point, what do we have? I have 866 grams of liquid water at 0 degrees. So what's the next thing I need to do? So now I have 866 grams of liquid water at 0 degrees C. So what do I need to do next? Remember, at the end, I want to have liquid, I want to have vapor, I want to have water vapor, I want to have gaseous water at 147. Right now, I've got liquid water at 0. So what's the next thing I need to do?
Heat it to 100 degrees Celsius?
Exactly right. So I need to take that amount of water at 0 and I need to raise it to 100 degrees C. Is that a heat capacity question? Okay, ask yourself 2 things. Is the phase changing? Am I changing the phase during this process? So I'm taking liquid water at 0 degrees, and at the end I'll have liquid water at 100 degrees. So am I changing the phase of the water?
No.
No. So that's not a, so that means it's not a fusion, it's not an evaporation. Am I increasing the temperature?
Yes.
Yes. So the phase isn't changing and I'm increasing the temperature. That means heat capacity. And which heat capacity am I dealing with? Am I dealing with ice, water, or liquid water, or steam?
Liquid?
Liquid, right. So now I need to figure out how much heat it takes to get 866 grams of water, and that's liquid water, so its heat capacity is 1.84 joules per gram per Kelvin, and I need to raise it by how much? What's my delta T? There's my mass, there's my heat capacity of liquid water. All I need left is what's the change in temperature? Right, Sean's right, it's 100, right? Because I'm going from 0 to 100. So my change is plus 100. So my Q is 866 grams times 4.184, my heat capacity, times 100. So that is 36, it's a lot. 362,334 joules, or 362.3 kilojoules. That takes a lot, because remember, liquid water has pretty much the highest heat capacity of any substance. So it takes a lot of energy to increase it. So now, what do I have? Now I have 866 grams of liquid water at 100 degrees. What's the next thing I have to do? So I have liquid water at 100. I want to wind up with gaseous water at 146. So now that I have my liquid water at 100, what do I have to do with it?
Need to increase its temperature to 146.
Nope. In order to get liquid water at 146 degrees, I would need to increase the pressure. But this is all being done at 1 atmosphere. So what am I actually doing to the water at 100 degrees? What's happening to the water at 100 degrees? It's going from a liquid to what? What happens to liquid water at 100 degrees? Something magical happens. What is that magical thing that happens at 100 degrees?
The water turns into a gas.
That's right. So I need to boil the water. Next, I need to take my liquid water and convert it to a gas, also at 100 degrees. So that doesn't happen by itself, remember. You need to keep adding heat in order to convert all that liquid to a gas. You need to break all of those hydrogen bonds that liquid water has. Even at 100 degrees, it still has, some hydrogen bonding going on. You need to break all those completely in order to turn it into a gas. You need to keep adding heat to do that. So we need to figure out how much heat does it take to do that. So again, we're going from a liquid to a gas. So we are doing a phase change, and we are not changing the temperature. So is this a heat capacity problem? Do we need to consider the heat capacity of liquid water or gaseous water, liquid steam? Do we need to consider the heat capacity of either one? Sean says no. How come? Why isn't this a heat capacity issue? What do we use to solve for Q then? If we don't use heat capacity to solve for Q, how are you going to solve for Q? So how do I solve for Q for this step? I have liquid water. That's right, Dennis. That is the delta H vaporization. Because I'm literally vaporizing liquid water to gas. So because it's a phase transition, I can't consider the heat capacity because I have two things at the same time. I have liquid water and I also have gas. And Heat capacity is not going to help me because the temperature doesn't change. I started at 100. I'm going to end at 100. So Q, if I for heat capacity, would be 0 because the delta T is 0. So it isn't a heat capacity issue. It's the heat of vaporization issue. And so I need the heat of vaporization. And since it's delta H, it means per mole. To figure out Q for this, I need the heat of vaporization and the number of moles that's undergoing that vaporization. So Q now would be the heat of vaporization for water, which is 40.1 kilojoules per mole, and the number of moles. And if you remember, we calculated that at the beginning, and it's still 48.07 moles. Take out the moles, and that is 40.1 times 48.07. So that's 1,927.6 kilojoules. So a lot of energy. Takes a lot of energy to boil water. You probably noticed. So now, what do we have? We have 866 grams of water vapor, right? We started with solid ice at minus 15, and we finally turned it into 866 grams of water vapor at 100. So we're almost home. What's the very last step we need to do? We just have one more step. That's right, we need to heat the gas from 100 to 146. So we need to take that same amount of water vapor and increase its temperature to 146 degrees C. Is that a heat capacity question? Yes. Why? Because we're not changing the phase. Still a gas. I've got gas at one temperature and I'm changing it to gas at a higher temperature. So that's a heat capacity question. The phase isn't changing, but the temperature is. The temperature is changing. That is a Q equals mass times heat capacity times delta T, because there's a delta T in there. Notice that the dead giveaway for heating, for melting and boiling is the temperature doesn't change. And if the temperature doesn't change, heat capacity is useless because it doesn't change. So it'd be 0. So in this instance, the temperature does change. So in order to solve for Q for this one, we need the mass times the heat capacity times the change in temperature. Well, what's my mass?
$866 grams.
Yep. Still got the same mass. It was ice, then it was liquid water, now it's gas. But conservation of mass. We haven't done anything to it except changed its phase. So I still have 866 grams. Now, here's the tricky part. What's the heat capacity now? Is it 4.184?
Is it 1.99 joules per gram?
Right.
Yeah, that.
Joules per gram per degree. Because that's the heat capacity of steam. The heat capacity of steam is different from the heat capacity of liquid water, and it's different from the heat capacity of ice. Because it all has to do with how those molecules are arranged. they're arranged in one way, higher heat capacity. Arranged in a different way, lower heat capacity. So now the molecules hardly interact with each other at all. So it doesn't take as much energy to increase the temperature. And then the change in temperature is just 46 degrees. So my Q now is 866 times 1.99 times 46. So 79,274 joules. So now I got 5 numbers. 1, 2, 3, 4, 5. Those are all 5 numbers that we've calculated. That's the amount of heat to melt the ice. The amount of heat to increase the ice from minus 15 to 0. Then we had to melt it. Then we had to increase the temperature of the water to 100 so we could boil it. Then we had to boil it. Then we had to increase the temperature from boiling to 147. So 5 steps. That's why this is a long question, and why I would, I would leave this kind of question to the very end on a test if I were you. Make sure I do all the easy ones first, because this one takes just a ton of calculations. So now I convert everything to kilojoules because I need to be adding the same thing. So I got 26.37 kilojoules. I've got 288.9 kilojoules. I got 362.3 kilojoules. 1927.6 kilojoules. And oh, unfortunately, I erased the last one. What was the number of kilojoules for heating up the steam? What was the number? Oh, I got it right here. 79.27 kilojoules. And I just add all of those together. And that's your final answer. Okay. And then as far as considering the significant digits, there's probably like 3, I think. Or maybe 2, because I think the temperatures, yeah, minus 15 only has 2 significant digits. So I would round to 2. You can see it's a long question. So just the tricky part is remembering the difference between the phase transitions and the heating. Phase transitions are delta H fusion or delta H evaporation. And whenever you heat something, you need to consider its heat capacity. When you're melting or boiling something, you're not changing the temperature. And then the other thing to remember is get the right heat capacity, because the heat capacity for liquid water, solid water, and gaseous water are all different. So make sure you get the right one. And then knowing when to use moles and when to use grams. So there's a lot going on in this problem. So anyone have any questions about this one? I know that it's a lot going on for this one. This one probably takes as much work as answering all the other questions combined.
I really hope this question isn't on the exam.
Well, like I said, this is the sort of thing I put on as a bonus. So let's hope, let's hope you get a bonus or something. Because this is a bonus question. Because it takes what, like 20, 25 minutes to solve. So when you've only got 2 hours, yeah, it should be worth more than 5 points or something. If you're only getting 5 points for it, I probably would just skip it. Unless you got time left over at the end. Yeah, just put it at the end. Solve all the other easier ones first. But you can see it's not really hard. it just takes a lot of calculations. And there's a lot of things that can go wrong in all those calculations. So yeah, there's a lot to remember. There's a lot of moving parts. All right. I kept you guys forever. You're probably late for whatever it is you need to do. I'm late for walking my dogs. So next week, I will send out a review, probably on the weekend, and then we'll do it together next week, okay?